Hello everybody. So in this session we're going to get the Linux kernel, the stable Linux kernel 4.7.6, and we're going to go ahead and configure the kernel to work for our BeagleBone Black. Our configuration is going to be brief as it's a very involved process and it would take potentially an hour or so to actually get it to work. And so I'm going to be giving you pointers about this process and provide a default configuration in my GitHub repository. We're also going to work with the DTS file, the device tree file specific to the BeagleBone Black, and I'm going to modify the default device tree for the BeagleBone Black to work with my LCD panel. We're going to remove the functionality of HDMI and add in the required device tree nodes to have our panel work. We're also going to be working on building a very basic file system with the basic frame buffer test application that will help us verify that our electrical connections and kernel configurations are correct for our LCD. Of course, for that to happen, we're going to have to compile our kernel. We're going to have to also add U-boot configured to work for the BeagleBone Black. We'll end the session by a test that verifies that our LCD module works okay. So let's get to it. Okay, so here we are on my desktop. I thought that before we jump into the kernel, maybe we should get a bit familiar with the hardware connections, just to know what we're actually doing, since this is an embedded system workshop. This is the datasheet that I spoke of in the first video, and we're basically looking at the pin header, the one that is not soldered, the one to the far left of the old development board I showed you in the last video. And it basically lists down all the pins and what they mean and what they're connected to. This is some good information here. Without it, you probably can't do stuff. You can't really connect this thing. So I'm thankful that I could actually find this, because although the display timing parameters are missing, and I couldn't find those anywhere, this is actually, at least this can get us past the hardware barrier. So now we know what to connect. And through the process of development, I basically extracted this information from the Bone Black's documentation. You can see that it's just a list of what it means. The first row tells me what LCD data bit does this thing represent, and what color bit, in this case red 3, and which pin exposes it. So this is pin 45 of the P8 header on the BeagleBone Black. So this information is enough for me to make the connections, or the correct connections. So just as an example, let's take the first. D0 means LCD data 0. That's what you will find in the BeagleBone Black. I keep saying BeagleBang. Anyways, BeagleBone Black's datasheet, and when you're, it represents R3. That is also from the BeagleBone Black datasheet, or was it from the errata? I'm not really sure. Maybe it was from the errata. Anyways, so it represents R3. And it is exposed through pin 45, which means whatever pin that represents R3 on the LCD module side, it needs to connect to pin 45. So we can go back to the datasheet and see where's R3. This is R3. It connects to pin 24. So let's go back here and see, yeah, it connects to pin 24 of the LCD side pins. So all this stuff I just extracted from the datasheet, and I wrote it down because there's, well, too many wires and I don't want to get lost. And I've done it a number of times. You see here 100%. This means I'm 100% sure this line here represents the correct color, the correct pin, and the correct pin on the cape. Let's just call it cape for now. It's that old development board that I have, and that it represents the pixel clock of the LCD. I went through this multiple times. Okay, so this is basically it. And at the side of somewhere on the screen, you will be seeing the actual connection. And yeah, it's a messy setup, but it works. Okay, so we're going to create a directory right next to the directory I created for the workshop, and we're going to call it workshop. I'm going to cd into it, and we're going to go ahead and clone the stable kernels repository. I have it off screen somewhere. All this stuff will be available on my public Git repository, so make sure you grab it. Or you could just head over to kernel.org and figure your way around. So this thing's gonna take some time. I'm gonna pause the video here and see you guys in a minute. Now that our cloning process has finished, we're gonna go ahead and rename Linux stable to Linux because that makes more sense. And we're gonna create a bash script that will help us set up our environment variables without passing a million command line arguments to our make. We will start off by creating a guard that will force us to source this bash script rather than running it, because of course if you run it, it won't set your environment variables. We're going to use the bash source environment variable for this to detect whether we're running the script or sourcing it. Your version of the shell might not support this, so you have to look into that. Mine happens to support it, so you got to look into that. If it's not really necessary, it's just a good thing to have. It's a nice feature to have. So you should make a habit of it. And then we're going to export our arc variable. It's the only variable we need in the configuration process for the kernel. We're going to revisit this script multiple times as we need to. Let's check everything's okay. That's it. We're gonna have to make it executable. And let's move on to test it. Let's first try to run it. It says no, you need to source me, which is expected. Then we're gonna try to source it. And there it goes, good to go. So now we're ready, as our arc variable is set. There, it says ARM. We're ready to go ahead and configure our kernel. So let's go do that. Let's first check whether our architecture environment variable is set or not. Yep, it is set. So let's just make menu config. Note that you only need arc you don't really need cross-compile when you're configuring your kernel. So what we're going to be doing here is a pretty involved process. There are multiple ways you can go through this. You could, if you'd like, you could start with the default configuration provided by your vendor, or a default configuration within the kernel, or you could go the way I'm going this way, starting from a vanilla configuration for your architecture, and just go through the configurations one at a time. Of course, this will take a lot of time, but it will help you when things get complicated later. If you have any failures running your kernel, you're already familiar with the configurations you set, and I'd encourage you to do that at least once, so you can get familiar with the configurations available. This is going to take well over 30 minutes, and it's probably not going to be the final thing. I'm going to try to run it, and it's going to fail, and then come back to the configurations and go through it once again. So this could take a lot of time. This could take, well, if things go wrong, it could be hours long. So I'm going to speed up this process, and but I'm going to give you some pointers. Basically, what you're trying to do is, of course, you have to get your system type right. This is very important. If you don't, you really nothing's going to work. And that's where you start. Just drill through each and every setting or configuration and see if you need it. You probably have to go back and forth between your documentation and this menu config interface until you get every single thing right. The things you need to pay attention to are, of course, like we said, the system type. Then goes your, of course, serial console, because without that you can't even see the errors that you'll get. You should also pay attention to a timer subsystem. So your SoC is getting its time from somewhere, and that subsystem within your SoC needs to be configured correctly. Without it, of course, you're going to get the same issue as if you did not initialize your serial consoles or configure your serial console correctly. You basically won't see anything after your bootloader's message. Another thing you need to keep in mind is the clocking subsystem is one thing. The pin control subsystem, specifically for this processor, for AM33, whatever, the pin control system is very, very important. If you get that wrong, you're going to have, again, the same exact result as if you did not set your serial console correctly, because, well, there's a certain initialization order that needs to happen with regards to the pin controls, to the pin muxing. So you need to get that right. How do you get that right? You compare your pin control subsystem from your datasheet, from your product's technical reference manual, and you come back here and look for the configurations that match. Basically, everything you're going to be doing is exactly that process. You got to figure out what your SoC needs configured into the kernel, and then come back to this interface and configure it in. There are things that are very important for loading the file system, for example, like your networking system. You have to set up your NFS system correctly. Make sure you have NFS3 client configured, because NFS4 is not yet functional in that way, in loading the root file system over NFS. Also, with regards to the networking system, you have to configure in the correct Ethernet chip driver, and you have to go through the IP configurations and all the specifically the networking stack options that are under, I think, networking or something. The TCP/IP networking stuff. You also have to pay attention to your file system configurations. Those are important. If your root file system is an ext4, for example, ext4 type file system, Linux file system, then the kernel has to support that. You basically go through these steps one by one until you reach a point where you can actually load your kernel and you can see the early print K messages. You should also set up your debugging log levels. Early print K, those things will be important when you're starting to develop using a new system. That's all that comes to mind. My configuration will be available on my GitHub repository. I'll link to it in the description box below. So you can check it out. You can run diff against the vanilla kernel and the vanilla kernel .config file and the default configuration that I will make available. And you can go through them and see which options I configured and which I left out. I'll try my best not to have any bloat, but I can't guarantee that. There are things that I'll probably miss and just configure in, and it's gonna make my kernel bigger. But all in all, it should guide you through the process of setting up stuff. Good luck with that, and see you guys when this thing ends. Okay guys, I'm not sure why this guy is saying your configuration changes were not saved. It's very strange. This Does it mean that it's not? Okay. We're gonna have to go back and check, because this would be a problem. I spent too much time doing this stuff. What pointers do we have? System. Let's see. Something that was not by default configured. Okay, let's just go here. Okay, I configured that in, and I did this. So it was written to the .config file. So we'll just ignore that. Anyways, if you've noticed, we've been working with the master branch of the Linux stable kernel, which is a mistake. We're gonna work on fixing that. See if we make kernel version. You'll see that we are working with 4.8 point some release candidate. That's not cool. So we're gonna save our configurations, just so that we won't have to redo them when we check out the stable branch. And let's just, okay, let's save those configurations in a separate directory so that I can share them later with you on GitHub. Let's view the tags. Look at that. That's my provider spamming me. Okay, what do you mean no git tag? Okay. There. 4.7.6. That's what we should have been working with from the start, but I'm clumsy like that. So we're going to check out a new branch. We're going to name it Bone Black. And we're going to base it off this guy. Okay. So let's view our kernel version. As we'd expect, it's 4.7.6. Now we have to transfer our configs over to this guy. What we're going to do is we're going to copy it into .config. Actually, let's copy it to the proper place for default configurations, which is for ARM processors, so ARM configs. We're going to name it Bone Black diffconfig, and we're going to use it as you would use any other default configuration to copy over the stuff to your .config. Now let's go the paranoid way again and check if our arc is not set. So we wanna check our configurations manually just to see if nothing was left out because of the kernel version change. Okay, let's what do we want to do? Let's make default config again after we've set the arc. Now let's check. We start with the system type, TI OMAP common features. Okay, this is set. This is set. What is this? PM layer. Yeah, whatever. Let's see here. Okay, I set this and it was transferred correctly. So we're okay here. Let's look for some configurations here in device drivers. We're primarily looking for character devices. Where is that? Network input. Character devices. Okay. So let's just check our serial console. Okay, all good. So we're now going to go take care of our DTS file, our device tree file for the bone black. We have to first, let's first vim into the file in question that is specific to the Beagle bone black. It's in ARM boot DTS AM335X bone black. Okay, this is the default file, and we're going to have to modify our pinmux, this guy, this device tree entry. And of course, you have to map this change by, okay, we're going to remove HDMI here and use our own thing for the panel, for the LCD panel. Of course, you have to map this change in the configuration. So your pinmux has to be configured in the kernel. I think it's under device drivers. Okay, let me copy over the DTS file that I created for the workshop, just so we save some time. Anyways, you have to reflect your use of the pinmuxing subsystem in the kernel configuration. I think it's under device tree GPIO or something, device drivers GPIO or something like that. So just make sure you configure that in. So we've copied our bone black DTS. Let's view it again. You can see the changes here. I've added a backlight node and a panel node, TI-LCDC panel. You can get all this stuff from the bindings documentation. If you check this node here, it's almost identical to the stuff we got from the bindings documentation, or I got from the binding documentations. The display timings are, okay, this stuff I got off of the source code of some kernel that was provided by the Chinese company that made the LCD, or the module that I'm using, the LCD module that I'm using. And for the clock frequency entry, I went with a very simple way of calculating the required frequency, which is basically multiplying the width by the height by the frame rate. It's a very basic way of doing things. If you have access to the timing documentation of your LCD panel, you could probably do a better job. Let's see what else we have. Okay, your PWM. This PWM entry is used by your backlight. And here's the thing: if your backlight is not configured correctly, your okay, we have the LCD 24 pins there, and the PWM backlight pin. If your backlight is not configured correctly, your TI-LCDC driver will not function. Check that out. The SGX node. This does not actually exist by default in the Linux kernel. It's supposed to be in ARM boot DTS am33xx.dtsi. It's an included file in this thing. You're not going to find it here. It's because it's related to a closed source object. So what we're going to be doing, I actually got it from, I don't really remember what I got it from, but it's all over the place. I got it from TI's SDK. So we're going to go, I'm going to go show you where this thing, or how it looks in, okay, let's vim instead of CD. SGX. We're going to copy this guy over to our own kernel. I got it. I mean, you'll have access to it. It's in TI's SDK's kernel 4.4.12. But since I have it here, I'm just going to, okay, let's set no number so we can yank it. Transfer it back to our own kernel. And format. Okay. You see, since you're actually turning it on, you see the status there, it's disabled. You're turning it on in your Bone Black specific DTS file. So it has to exist in an included file, otherwise you'll get an error. So that's how you know it's missing. Okay. Yeah, let's get out of here. And out of there. Okay, now that we're done with all that stuff, we're going to have to deal with some inconsistency that was introduced to kernel 4.7.0 actually. And I'm going to go show you what this inconsistency is. If you look for the PWM entry, the one that we're turning on for our backlight, it's down here. Where are you? Okay, here it is. You'll see that the this thing says PWM, right? And for this reason, the kernel will be looking for this exact thing. Whatever part of the kernel that uses, and we're going to go see it now, so it's in clock TI. Whatever part of the kernel drivers that actually uses this entry expects to see some address dot PWM. But let's look at what's in the kernel there. The address dot EHRPWM, which was the case in a previous kernel, but then the change was introduced to the device tree, but not to this file. So we're going to have to patch this file to actually match the change that was not introduced. So we're going to go, we're going to make a directory for this patch, and from now on, all the patches we introduce to the kernel will be saved here. I'm going to copy it over from the workshops directory, the live workshop that I did. I basically got this off of some mailing list. Well, we don't have the time to go look for it right now. So there it is. See, it introduces the change that was supposed to happen but was not introduced on time. I read on that same mailing list that this change will be introduced in 4.8, kernel 4.8 stable. So if you're working with that, you may not need this patch. So we're going to apply this patch, remove the first directory, and there we go. So let's go check out the change we made. What is it in drivers? Clock. Is it C? I think yeah, CLK. TI clock 33xx.c. Okay, let's search for what was it? EHR, whatever. Yeah. So these three lines were introduced. So the driver will find the node that it expects. Okay, at this point, we're gonna need to go get our compiler, because so far we didn't really get to that point yet. The compiler we're going to get is, you can actually go straight to Linaro or maybe build your own cross-compiler if you're into that kind of stuff. But the way we're going to do it is by basically going over to buildroot and getting a compiler that is coupled with buildroot, so that it would help us build user space packages later without having to, jump through hoops. So this is not a requirement, but it's a very nice thing to have, a central place to control all your build stuff. So we're gonna go get our buildroot source. We're gonna basically clone buildroot's repository. Download. You could just download this and extract it, but I'd like to have a reference so that if we were to update, the process will be a lot easier. So let's just clone it. And let's use Git's own protocol. And we're gonna use buildroot for a lot of stuff. A lot of it is not strictly necessary, but you want that. You want a central place to actually go fetch all the stuff you need: the userland packages, your bootloader, your basic root file system. So we want buildroot to be our central build management tool. And okay, there we have buildroot. So let's cd into it. And it looks a lot like the Linux kernel, or maybe more like U-boot. Let's echo arm. Okay, we don't want arc to be set when we're working with buildroot. I'm not very sure about this, but I don't think it should be, because buildroot expects you to work with your host system's configurations. So let's make menu config. I'm not very sure about this, but I think it makes sense. Let's change the architecture. And Cortex A8. This will be Neon. Toolchain, okay, that's what we're here for. Linaro something something. That works for us. Anything else? No. System, bootloader, none of that. We're going to build the root file system and the U-boot, the bootloader in their own context. Oh. We made the mistake, the same one, of course, of working with master. You don't want to do that. Let's just get the stable 1.8.2016. Now let's see let's check out our configuration again, just to make sure that things are in check. Okay, this is check. I think let's check the toolchain. All right, toolchain is okay, so we can just make. Let me speed this thing up. So buildroot is done, and it produced a file system That will always happen. But we're here for specifically the compiler, which you'll find in output host user. There it is. If you go to binary, ls, this is the stuff that you need in your environment. This is what you're going to set your cross-compile environment variable to. So we're going to go to our setup script and add the stuff to our script. Let's set our root directory, just so that we don't have to type this every time. Development, project, BeagleBone, and workshop. So this is the root directory of our workshop. Let's set buildroot's top directory. Okay, and our compilers directory, which is under buildroot. Output, host, and user. Okay. So we're going to first check if our compiler directory is actually, or does, it actually exists. So, and if it doesn't, then we won't try to set anything, and we're just going to print out a message. So if it exists, then we're going to export path. We're going to add the compiler dir to our path. We're also going to export okay, let's just put this guy here. And we're going to export, what else? Cross-compile. I'm going to set it to ARM, Linux, GNU, EAB, hardware float, and the dash there. What else? What else do we need? Do we need anything else? No, nothing. So for now, we're going to stick to this. Else, if it's not a directory or it's like it does not exist, we're going to say compiler directory does not exist. And we're going to ask, did you run make in buildroot? Because if you didn't, then you won't. That directory will not exist. Now this is of course only one possibility for this error to be, or for the cause of this error. Okay, let's take this guy right there. But it's the most probable. So let's save it. Check. Everything's fine. Get out of it. Clear. And try it out. Great. So let's see this. Okay. All is set. There we have Linux. ARM none is something I have in my bash script, or my bash RC. Anyways, so now we can actually get to building our kernel. Now that we have buildroot and our compiler set up and everything, let's go ahead and download uboot and configure it to work for our BeagleBone Black. Let's check first for our arc, because we don't want it to be set. All good. Let's make menu config. And we're looking for bootloaders. Where is my bootloader? Is it target? Bootloaders, okay. And we're going to go with uboot. We're going to set this to kconfig and keep this. We don't care about this. Yes, we're using this. And the board config, okay, we're going to go to uboot source and find out which default configuration corresponds to the BeagleBone Black. So uboot here. We want the source code. Git. And we're looking for tree configs C. Where are you? There. And we're going to search for AM335, okay. Bone Black, there. Okay. We're going to set this to that, without, of course, the def config, default configuration. You don't do that. No, it doesn't. uboot.image. And I'm going to go with, okay, if you read the help, you'll see that it says MLO on OMAP. So we're going to use that. Okay. This, that, none of that. Okay. File system. Okay, let's just go ahead and create our basic file system so that we don't have to come back here again. I mean, we're gonna have to come back, but let's just set up the most basic stuff that we know we need. So we want libdrm. Where are you? Hardwares and libraries, graphics, there, libdrm. We want the test suite. And OMAP. I'm not sure this is needed, but okay, because we're using TILCDC, not really OMAP DRM. Anyways, do we need anything here? I think we're good. But we still have to go to BusyBox, specific menu config. So how awesome is this? It's just as if we're actually using BusyBox standalone. Anyways, we need some kernel modules utilities. Okay, where's Linux module utilities? There. We want what? depmod. There's a need for it later, and we'll get to it. So we're good. We're ready to build. Actually, before we build, let's. There's this package that I use to test my LCD setup. It's called frame buffer test. Let's go get it. Of course, it will work because of the emulation. We're using DRM, not frame buffer, but TILCDC driver actually emulates the frame buffer functionality, so it's backwards compatible. This test application does not actually do things the DRM way, but because of the emulation thing, it just works. So let's make. So we're done. Let's go ahead and check out the output that buildroot produced. We'll find that in output images. No, that's it. There you have it. MLO, root file system, and uimage. So MLO and uimage are going to our SD card. So, and the root file system is what we're going to provide through NFS or load through NFS. So let's get to our SD card. It's already formatted. You can find the information about that all over the internet. So I'm going to copy this guy because we're lazy. And we're going to cpmlo to run. I don't think, I'm not sure I agree with that, with mounting stuff over at run. Media, okay, media makes sense, but run makes no sense to me. Anyways, so we've copied both our MLO and uimage. Now we're going to create our uenvironment text, which is something that the BeagleBone Black expects for its U-boot. Well, U-boot expects for this the default configuration of this thing. So we're going to set our root to dev nfs. That is just a shim. It's a not a shim. It's a pseudo file system to tell the kernel to actually 0.106 to actually use or load the file system over NFS. Our root path is server NFS4 root fs. NFS4 is just a name, so it's not really 4. We're using NFS version 3, but I was working on something else and it's just there. I named it that. So NFS load TFTP echo. Okay, this is a command. Load TFTP is a command that we're gonna run later. So the first thing it's gonna do is basically print out TFTP yin, just to tell us that okay, this thing's working and I am reading that. It's gonna run DHCP and then TFTP image. Just gonna load the Z image to the load address of the kernel, which is default. It's configured into the def config that we added. And so is FDT address. So we're gonna put AM335X Bone Black DTB into FTP address and zimage into load address. Remember, zimage and that DTB file are boot arg set. That zimage and that DTB file will be provided over TFTP. So we have to copy these guys to console. Okay, we're going to use the default configured console in U-boot. We're not going to set it here. I think it's UART0 or TTY00. That's what it's called here. Ignore log level because we want all messages to be printed. We're going to set our root to dev NFS, which is defined up there. What else? Okay, we're going to set NFS root and use our server IP. Root path. We're going to specify NFS version to be 3. This is important. I think it's the default, but whatever. And the protocol to be TCP. You don't want UDP there because it's problematic. And whatever is in NFS opts. We could have actually put all these options in NFS opts, but I just went ahead and did this. W size 8192 read write. You could read all this stuff that because our IP will be IP. We're doing that because if we are to set IP to a static thing, then it would just work. So we're gonna call the stuff the commands we wrote. So we're going to say print out booting from network, setting boot args. So we're going to call boot args set first, run boot args. You see what happened there? This is boot args, this is boot args. We're defining it and then we're running it. So just this is basically all we're going to be doing with all the commands we set here. And then we're going to run load TFTP. See there? Load TFTP. And that's the definition of the command. So it's just going to take that variable, extract it, and run whatever it finds in it. What else? We're going to echo booting. And these are commands we're going to just plug in here. We use bootz, load address dash FTT address. And basically that's all we need. Okay, we've created this next to our MLO and U-boot image. We'll show you there. They're all sitting next to each other in the boot section. The root file system is, we're not going to touch it here. We could load our root file system here, but we'd have to, keep loading it with every change, and that's not something you want to do. Okay. So now that we're done with this, let's go ahead and build our kernel. I've actually built the kernel multiple times to set up the configuration, but I'm just gonna go clean it and start the whole thing again. It was necessary to basically get the configurations correct Of course, you can grab those from my repository. Links in the description. See, it's only gonna make the modules and whatever changed, but nothing really changed. So I'm gonna clean it. This does not hurt our configurations, so we don't have to worry about that. So let's just make. So our kernel is done building, and we have everything we need set up. So let's just start our servers. This will be different for you if you're not using system control or sysd. I'm going to start NFS server, TFTP, and RPC bind. You need those three services to get this whole thing to work. The NFS, specifically the NFS, you need RPC bind and NFS server. And for your Z image and device tree blob, or binary, you need TFTP. So let's check the status, because we don't want typos there. All of them are active, all of them are running. Okay. So we're gonna go into Minicom. Again, you can use whatever terminal emulator you're familiar with. And let's turn on the BBB. Look at that. Going good. Okay, we're loading the kernel. Loading the kernel again. This is strange. I don't know why that happened. Okay. We have some mounting errors there. Let's just log in. Look at that. Never mind. That's a configuration thing. Okay, here's our file system. We're gonna have to go back and fix some stuff, so let's just test our mode test. It works. Okay, this should work. And our frame buffer. Because you see, we're gonna have to go fix that double loading TFTP thing. Okay, this works. We're going to see the effect of it later, but for now, we just want to see if our software works. And then we have that tempfs. It's probably a kernel. It's probably a kernel configuration issue. I did not enable the configuration of tempfs. That I'm going to have to go do. Okay. Okay, let's remove the TFTP from our boot environment text. Where is it? The Z image TFTP, because there seems to be a default configuration that causes U-boot to just TFTP Z image. So we don't want to do that. And we're going to start again. Reboot. Okay, loaded only once. That's what we wanted. Okay, I forgot the tempfs thing. Never mind, we can do it later. So let's actually test our the effective mode test on the actual screen. And let's go with our frame buffer test. There, that is expected. We could also test offset. What does this do? Okay, it needs argument. We're going to ignore it because we don't want to read or understand. Let's try rectangle. Oh, this is jolly. I never actually ran this before. Anyways, I think that this basically tells us that everything works. What is this? Performance? None of that. Okay, I think we're gonna conclude this session here. It took almost an hour, but we know that our libdrm setup works, our electrical connections work okay, our frame buffer setup, the emulation of DILCDC for frame buffer works okay, and I'm sorry for producing such a long video. I could not avoid it. I'll try to keep the next videos shorter, and see you next time.